Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 69, and it is entitled Nuclear Reactions and Equipotential Lines. This lesson is divided into two parts, which are unrelated, and we'll take each part in turn. The first part deals with nuclear reactions. Whether you know it or not, your life is daily impacted by practical applications of nuclear reactions. In Stoddy Daisy, the Tennessee Valley Authority operates the Sequoia Nuclear Power Plant, supplying the vast majority of Chattanooga's electrical power. Sure, hydroelectric plants generate electricity at Chickamauga Dam and Nickajack Dam, and the Raccoon Mountain Pump Storage Hydroelectric Station works during peak demand times to help satisfy our hunger for electrical power, but the lion's share of our region's energy comes from Sequoia. The nuclear fuel for these reactors is the radioisotope uranium-235, a fissile isotope that releases two or more neutrons when a single neutron collides with and splits the uranium nucleus. This is the same isotope that was used in the first atomic bomb dropped on Hiroshima, Japan, near the conclusion of World War II. Sadly, another application of nuclear reactions includes atomic weapons, one subset of a larger class known as weapons of mass destruction. The militaries of several developed nations possess the technology to unlock the strong nuclear force and apply it toward destructive ends. This complex, secret technology is actively sought by nations such as Iran and North Korea, which wish to join the so-called Nuclear Club of Nations. Their efforts are the subject of intense political concern, leading to tension among world powers. The image on the left illustrates the casings of the weapons used by the United States against Japan, namely Little Boy, using uranium-235, and Fat Man, which employed plutonium-239. To get a sense of scale in these models, the height of the Fat Man weapon is about 5 feet tall. Another military application of nuclear power lies more along the lines of TVA's Sequoia Nuclear Station, and that is using nuclear reactors to power the propellers of submarines and aircraft carriers. Starting in the middle of the 20th century, militaries around the world began building large ocean-going vessels containing nuclear-powered steam generators to push these vessels around the ocean, using technology similar to, but much smaller than, that used in nuclear-powered electric generating plants. On a more positive note, the medical profession makes use of nuclear reactions too. Doctors, called radiologists, apply nuclear reactions in the branch of the field called nuclear medicine. Radionuclides relied on the process of radioactive decay in the diagnosis and treatment of disease. In nuclear medical procedures, elemental radionuclides are often combined with existing pharmaceutical compounds to form radiopharmaceuticals, which, once administered to the patient, can localize to specific organs or cellular receptors, allowing the ability to image the extent of a disease process in the body based on the cellular function and physiology, rather than relying on physical changes in tissue anatomy. In this image, metastasized cancer clearly appears in several locations in this individual. In some diseases, nuclear medicine studies can identify medical problems at an earlier stage than other diagnostic tests. Common isotopes used in nuclear medicine include fluorine-18, gallium-67, krypton-81, rubidium-82, yttrium-90, technetium-99, indium-111, iodine-123, iodine-131, xenon-133, and thallium-201. I don't expect you to know this list of elements, but I think it's interesting to see what it is that doctors use. Most of these isotopes are used for imaging purposes, but a couple of them have therapeutic applications. In your own home, I'll bet that your family has installed one or more smoke detectors. One common type, called an ionization detector, senses the presence of invisible particles, which are less than 0.01 micron in diameter, in the air using the radioisotope americium-241. Inside the detector, a small ionization chamber contains an extremely small quantity of this radioactive substance, which decays at a fairly constant rate, emitting alpha particles in the process. The alpha particles, traveling extremely fast, ionize or knock off electrons from the atoms in the air, consisting mostly of oxygen and nitrogen molecules, that happen to be passing through the ionization chamber. The free electrons from the air are then attracted to a positively charged plate in the ionization chamber. At the same time, the positively charged oxygen and nitrogen ions are attracted to a negatively charged plate, creating a very small but constant electric current between the plates. When combustion particles, or dust, or steam, or fumes enter the chamber, that current is disrupted because the electrons attach to these foreign non-air particles, thus dropping the current too low and triggering the alarm. The design of the detector includes limited amounts of radioactive material, ensuring that exposure is unlikely with proper handling. Alpha radiation, as opposed to beta and gamma, is used for two additional reasons. First, alpha particles have high ionization, so that sufficient air particles will be ionized for the current to exist. And secondly, they have low penetrative power, meaning they'll be stopped by the plastic of the smoke detector and/or the air. All of these practical applications of nuclear technology involve nuclear reactions, and that's one of the topics of today's lesson. On the AP Physics B exam, you'll be expected to recognize nuclear notation and to use it to balance nuclear reaction equations, a bit like chemistry, putting numbers on either side of a reaction equation and making sure that they add up. So let's remind ourselves of nuclear notation. The atomic number Z represents the number of protons in the nucleus. Why the letter Z? I'm told that the German word for atomic number is Atomzahl, so the Z presumably is German for number. Another number, the mass number A, gives the total number of nucleons, which is the sum of the protons and the neutrons in the nucleus. I don't know why the symbol A was chosen for the mass number. It turns out that elements have atoms that can differ in their number of neutrons, and we call these different forms of the same elements isotopes, symbolizing a particular isotope using a certain nuclear notation. The X in this notation stands for the symbol of the element from the periodic table. So, if I wanted to represent the fissile isotope of uranium, it's symbolized like this. So this means that there are 92 protons in the nucleus and 235 nucleons. If I wanted to find the number of neutrons, then I would have to subtract the two numbers. So uranium-235 contains 143 neutrons. Unstable atoms are called radioisotopes or radionuclides. This means that they naturally change by emitting alpha, beta, and gamma radiation, like we studied back in lesson 54. You'll recall we encountered these three kinds, which include certain particles, alpha, beta minus, and beta plus, and gamma, and we symbolize them this way using the nuclear notation. There are beta plus emission, also called positron emission, and beta minus emission, called electrons. We don't normally write any numbers with gamma radiation because when gamma rays are given off, the nucleus doesn't change its atomic number or mass number. Rather, the gamma photon carries away energy from the nucleus as it transitions to a lower energy level, much like an electron does when it makes an orbital transition from a higher energy level to a lower energy level and sheds the energy in a photon that can be seen spectroscopically. Notice there are several different notations that could mean identical things when people write it, so depending on who writes it, they'll use a different notation. So notice the different ways that alpha and beta plus and beta minus particles can be written. In addition, you'll also see some other common particles including neutrons and protons. Be careful that you don't confuse positrons and protons with each other. The rule when balancing nuclear equations is this. On the reactant side and on the product side of nuclear equations, the atomic numbers are conserved and the nucleon numbers are conserved. It's a simple balancing act, as we'll see in the following examples. Example 69.1. Refer to a periodic table and fill in the missing particle or nucleus. In A, I have isotope calcium-45 that changes into something that I'm looking for plus a beta minus particle plus a gamma. So I want to balance this. The way I'm going to do it is I'm going to see that I have to have whatever this question mark is plus 0, add up to be equal to 45. So whatever I get up at the top has got to be a 45, because 45 plus 0 plus 0 is equal to 45 on the left-hand side. On the bottom, I have 20 on the left-hand side, so I've got to have something that adds up to 20 on the right-hand side. I have a 0 down here in the gamma, I have a minus 1 there, so I've got to have a 21 as a subscript down here on the bottom, because 20 is equal to 21 plus negative 1 plus 0. So now whatever my isotope is, it's going to be 45 mass number and 21 atomic number. So I refer to the periodic table on page 1016 of your textbook. I find that the element is scandium 45. B. Neptunium decays into plutonium plus something, and I need to balance the numbers. So up at the top, I've got 239 on the left. On the right, I've got to have 239 plus some number. That number at the top is going to be 0. On the bottom, I have 93 on the left. I have 94 plus something has to add up to 93 on the right. That's going to be a negative 1. I can tell this is going to be a beta minus particle. Part C. Something on the left decays into polonium-206 plus 2 alpha particles. Now I need to be careful here, because you remember each alpha particle has a 4, 2, and I have 2 of them here. So that means that I have a total of 8 and 4. That is going to be added to the 206 and the 82 in order to get the numbers on the left. So 206 plus 8 is going to be 214. 82 plus 4 is going to be 86. So now I go to the periodic table and see what atomic number 86 is, and I find that to be radon, R-A-D-O-N.